Good morning, guys. Today we're going to wrap up our unit on sampling distributions by talking about the sampling distribution of sample means. So just like with proportions, it's a distribution. It's going to be a quantitative distribution. So it's going to have a shape, a center, and a spread. Let's talk about how the way we take our samples can impact what the shape, center, and spread of the sampling distribution is. So remember, sampling distribution is if we were to take all possible samples from our population of the same size, what would the distribution of all of those sample means in this case be? So very similar to what we looked at, this relationship between shape and sample size that we have with proportions. So just like before, when sample size is small, so with proportions, when sample size is small, our sampling distribution looked like the binomial distribution that related to that sample proportion, or to that population proportion. So when sample size is small, sampling distribution in this case is going to take on the shape of the mean. So that means that if I have a left skewed distribution, so left skewed population, then small samples are going to produce a left skewed sampling distribution. If I have a right skewed population, then small sample sizes will produce a right skewed sampling distribution. And if I have a symmetric population, then small sample sizes will produce symmetric sampling distribution. So it's just whatever you see in the population, you're going to see the same thing in the sampling distribution. Now what happens as sample size increases? Well, it's that same idea that we talked about. That binomial could be left skew, right skew, or symmetric from a proportion standpoint. As sample size increased on that, those tails where the small probabilities were kind of dropped off and we got that symmetric looking distribution. Same idea happens here. As sample size increases, the sampling distribution of a sample mean becomes more symmetric and normal. And we'll look at some examples of this in class. So how large do we need to get to be normal? Now, when we dealt with proportions or sample proportions, we had that large counts condition. If I could count at least 10 successes in a sample and at least 10 failures in a sample, then we knew that the sampling distribution for all samples of that size was going to be approximately normal. And when we're dealing with means, we don't have successes and failures. You just have an average that you've generated from your data set. So what we're going to use is the large sample condition in this case. Okay, so not large counts. Large counts is for proportion, so we want to make sure we get that vocabulary right. Large counts is when we're looking for normality from proportion. Large sample is when we're looking for normality with means. So to use a normal approximation for sampling distribution of sample means, I've got to have one of two things. Either the population has got to be normal, because we know that if we have small sample sizes, the population is normal, the sampling distribution is normal. Okay, so that's number one, check to see if the population is normal. And then two, if the population is not normal, then we've got to have a large sample. And how large of a sample do we need? What's our large sample condition? Well, it says that n, that's your sample size, is greater than or equal to 30. This is known as the central limit theorem. So that's kind of another vocab that will be thrown out there. Central limit theorem says, what's the minimum amount or minimum sample size I can go with to be confident that I can use normal approximations? Okay, so large counts condition, also known as central limit theorem, says my sample size needs to be at least 30 when we're dealing with means. Now, we're going to run into this large sample condition in other situations. So different situations require kind of a different minimum on your sample size. But we're dealing with means, and so if I'm just dealing with sample means, then I just need to have n greater than or equal to 30. N greater than or equal to 30. Now, some texts you'll see will say n greater than or equal to 40. Again, when you're getting into the calculus of when this thing becomes actually normal, there's a little bit of wiggle room and stuff in there, but we're going to use n greater than or equal to 30. Most things will be accepting n greater than or equal to 30. But again, there are situations where you may be required to have a little bit larger sample size. Now, that large sample size kind of comes back into talking about variability of the statistic and things like that. So we'll look at how that ties together here in a second. So shape, If it's small samples, looks like the population. If it's large samples, at least 30, it's going to be approximately normal. Let's talk center and spread. So center. So the center, or the mean of our sampling distribution, and we've already talked about this, the mean of our sampling distribution should be equivalent to the mean of the population. Why should the mean of the sampling distribution be equivalent to the mean of the population? Because we've already talked about before that this is our definition of an unbiased estimator. This is why we like using sample mean. We like working with sample mean as an estimate of population mean, because if we look at all possible samples and take their average, that should give us the average of the population. So that's what we're talking about with the center, just like it was with sample proportions. What's going on with all possible samples should be the same thing that's going on with the population. Now spread, again, standard deviation is going to be how we're going to measure spread. So our standard deviation of sampling distribution should equal this formula right here. So what do we notice here? We have a sigma x divided by square root of n. Well, what does sigma x represent? Well, sigma is standard deviation, x is our variable, okay? So that refers to the population. So sigma x is standard deviation of the population. Standard deviation of the population, and n should be representing, as it always does, sample size. So just like we did with proportions, remember when we talked about the sampling or the standard deviation of sample proportions, it was taking what was going on in the population, your expected probability of success, your expected proportion of this characteristic, and we put that and tied it into n. So it was square root of p times 1 minus p over n. So it was looking at what happens in the population based on what's your sample size is. So same idea here. What's going on in the population from a spread standpoint, standard deviation x, and then we're adjusting it for sample size divided by square root of it. So very similar to what we looked at with proportions, with that n being in the denominator, that sample size has a big influence on this standard deviation right here. Because if that denominator is really, really small, then the standard deviation, the whole fraction is going to be really large. If that standard deviation or that sample size is really big, then that means the whole fraction becomes smaller. So that's a good idea that we want to have in mind with all statistics, all measures that we're taking. So as sample size increases, variability of the statistic. That's a standard deviation of that statistic. Variability of the statistic decreases. So it kind of goes back to things we mentioned lots of times. If you want to get more consistent results, not have as much variability, you just need to have a much larger sample. So sample distribution of sample means, big ideas. If we have small samples, then they look like the population from a shape standpoint. If we have large samples, greater than or equal to 30, then the shape's going to be normal. Center of the sampling distribution should be the center of the population, and standard deviation of the sampling distribution should be standard deviation of the population divided by square root of sample size. That's it for sampling distribution of sample means, and I will see you guys in class tomorrow.